To wrap up a little bit from the last video about redox reactions, there are reactions that are non-redox, and the way you know if it's a non-redox is you, again, assign oxidation numbers. If the oxidation numbers don't change, then it's a non-redox, okay? And just remember that if you have an element, whenever you're assigning an oxidation number, they want to know what the oxidation number of each individual one. So if you have, for example, like we had with the potassium chlorate, 3 oxygens, yeah, you do the -2 times 3 to get -6, but the -6 is not the oxidation number of each element. -2 is the oxidation number of each element. So when you're comparing oxidation numbers, you're comparing the 0 to the -2, not the 0 to the -6. Just wanted to make sure you understood that. Okay, moving on to a new topic, collision theory. How is it that reactions occur? We kind of take it for granted. We mix a bunch of things. We get interesting colors. We get precipitates. We get gas being produced. But how is it that the actual reaction occurs? Well, the only way for a reaction to occur is that the reactants have to actually collide. And that's what the collision theory is. So the first thing in a reaction is that the particles, the reactant particles, have to collide. They can't just be floating around in a beaker and not hit each other. So they have to collide. All right, that's molecular collisions, activation energy. They also have to collide with a minimum amount of energy, and that minimum amount of energy is called the activation energy. So in order for a reaction to occur, the reaction particles have to have a minimum amount of energy to collide, and then they can become products. That minimum energy is called the activation energy. And the third key part is they have to collide with the right orientation. What do I mean by that? Let's say a reaction will occur only if my fists hit this way. Well, what if my fists hit this way? No reaction will occur. What about this way? Nope. What about this way? Nope. So they have to, the particles, the reactant particles have to collide. Number one, they have to collide. Number two, they have to collide with enough energy. And then number three, they have to collide with the right orientation, the right direction, okay? So that's your collision theory. Now, reactions could either be exothermic or endothermic. Now, we used those terms earlier on in a previous chapter. The term exothermic means that heat is a product. Heat is produced, okay? The term endothermic, that heat is absorbed, or you can think of it as a reactant. So the law of conservation of energy says that you can't create energy or destroy energy, you can only transfer energy. So when heat is produced, you're transferring the heat to the environment, okay? When heat is absorbed, you're transferring the energy into the bonds that are creating the product, okay? Now, in order to show if a reaction is exothermic or endothermic and to show this whole energy thing and the activation energy, we do something called an energy diagram. Energy diagram. And there's a different diagram for an exothermic reaction, different than an endothermic reaction. Because in an exothermic reaction, let's say you've got A plus B will give you AB plus heat. So this would be an example of an exothermic reaction where heat is considered a product. All the energy here is equal to the energy in these two. So if you just look at AB by itself, it has less energy than A plus B. Why? Because the rest of the energy goes off to the environment as heat. That's when, when you're doing a reaction in lab and you feel the test tube and the test tube feels hot. That's an exothermic reaction. So if I'm going to do an energy diagram, and I'm going to have progress of reaction this way, progress of reaction. Rxn is just reaction. And I have energy this way. And let's say the energy of A plus B is over here. So the energy of the reactants is here. AB, remember how I said, because all this is equal to this, AB by itself is going to have lower energy. So I'm going to put AB over here. Because remember, law of conservation of energy says that all this has to be equal to this. So the difference between this and this, that's the heat that's being produced. But remember how I said that you have to have the minimum amount of energy in order for a reaction to occur? We call that activation energy. That's like a hump that the reactants have to go over. So this hump, this thing over here, that's the activation energy. Activation energy. So you have to climb up this hill in order to get down to the other side. All right? The difference between A plus B and AB, this is the amount of heat that is released or produced. So this is a typical exothermic reaction energy diagram. All right? Now, what would an endothermic, so this one is exothermic. What would an endothermic energy diagram look like? Well, let me erase this. And with an endothermic reaction, heat is absorbed. So we go A plus B plus heat will give you AB. So we think of heat as a reactant here because you're putting it into the system. So you can see here that AB is going to have more energy than the original A plus B, because you have to add this stuff in order to get to this. Again, law of conservation of energy, they have to have the same amount. All right, so on both sides of the reaction. So we're going to do progress of reaction this way, and we're going to do energy on the y-axis. Okay, so we're going to put A plus B over here, just like we did before. But remember how I said now these guys absorbed energy in order to become AB. So AB is going to be up here now. There's your energy diagram for an endothermic reaction. Now this is endothermic. All right, activation energy. Remember, it's a hump. Now it has to go over and then down. So look at how high this is going to be. See all this. Here's my activation energy. So you can see how much harder it is to get over to the other side. Endothermic reactions need you to put energy in order to get over that big hump. Okay? And the amount of energy you have to put in is just the difference from this. We do something called a delta H, which tells you how much energy is either absorbed or released in a reaction. And this is something for those of you going on into higher level chemistries. Delta H of an endothermic reaction is always going to be positive. Delta H of an exothermic reaction is going to be negative. You will talk about when you start doing some thermochemistry. But the idea is that basically if you take the heat content of the product minus the heat content of the reactant, or the energy of this minus this, in an endothermic reaction, this is more than this, so that's why you get a positive. But in an exothermic, remember how AB was down here in an exothermic? This minus this would end up being negative. And the change in energy would be a negative number. Not the energy itself is negative, but the change in energy is a negative number. So delta H for exothermic is negative, delta H for endothermic is positive. Okay, so the next video, well, actually, maybe I can do it right now. The things that affect, influence the rate of the reaction. So no, maybe I'll just go ahead and wait and do that in the next video. There are a few things that will affect how fast a reaction will go, and I'll talk to you about how to measure the rate of a reaction, but how much it's divided up, how the nature of the actual molecules, the temperature, the concentration of the reactant. So we'll talk about those things in the next video, which will deal with rates of chemical reactions. Okay?